Welcome to the Ontario High School video podcast series on gas stoichiometry. We're into part 2 of this. In the previous podcast, we dealt with what to do stoichiometrically when you have a gas at SDP. In this particular podcast, we're going to look at what happens when the gas is not at standard temperature and pressure, and the use of the ideal gas law is required in that setting. So, welcome. Some of the first few slides are going to look the same. We're going to go through them rather quickly, but there may be some constants you'll want to write down and just some reminders. So here we go. Quick reminder, again, you can pause this at any time and write down what would be helpful to you. But standard temperature and pressure are the conditions under which the standard molar volume of a gas is 22.4 liters. So at SDP, 1 mole of any gas, doesn't matter what it is, occupies 22.4 liters. And SDP, again, as a reminder, the pressure is 1 atmosphere, or if it's expressed in millimeters of mercury or torr, it'll be 760 millimeters of mercury or torr, or in kilopascals, 101.325 kilopascals. The temperature, thankfully, is always expressed in Kelvin, and it would be 273 Kelvin. Pause this slide if you need to write these values down. We spoke about them in the previous podcast. Same with this. Pause the podcast if you need to write this value down. If you already have it written down, just keep going. Quick review of keys to gas stoichiometry. Get to the mole any way you can. If you're at SDP, of course, it's real fast. If you're not at SDP, use the ideal gas law. And of course, once you've found the moles of gas, fill in the BCA table and do what you're supposed to do. Let's look at a sample of stoichiometry problem involving a gas that is not at SDP. Here we'll start with 14 liters of chlorine gas, initially at 298 Kelvin. 0.987 atmospheres is reacted with 20 grams of solid sodium to form solid sodium chloride, NaCl. How many grams of sodium chloride will be formed, and how much of the excess reactant remains if the temperature after the reaction is 625 Kelvin and the pressure is 1.64 atmospheres? This is a very exothermic reaction, meaning a lot of heat's going to be released. So the gas that remains, the conditions under which the gas exists are not going to be the same as at the beginning, and that's what this reflects. So write down your data table and let's go. As with all our stoichiometry problems, when we're given a quantity of more than one of the reactants, we want to first find the moles of each reactant and then pursue what our limiting reactant calculation is. So to find the moles of the sodium, a very simple conversion, 20 grams of sodium times the conversion factor that would have 1 mole of sodium on top over 23 grams of sodium on the bottom of your conversion factor. When we do that, we get 0.870 moles of sodium. To find the moles of chlorine, because we're not at SDP, we must use the ideal gas law. So let's do that. In order to use PV equals nRT, we're going to be solving for N, which is the number of moles. So we're just going to write down what we know we have. Our pressure is 0.987 atmospheres. Our volume is 14 liters. Our temperature is 298 Kelvin. And our R value, because we're in atmospheres, is 0.082 liters times atmospheres divided by moles times Kelvin. Now, I wrote that as moles to the -1, Kelvin to the -1, so I could write it on one line and be a little easier. But it's liters times atmospheres over the product of your moles times your Kelvin. We're going to rearrange the ideal gas law, PV equals nRT, and we're going to rearrange that to solve for N. So we're going to divide both sides by RT. When we do that, on the right side of the equation, the RTs will cancel, and then we will have N is being equal to PV divided by RT. Since we have both our base equation and now our working equation, which is the rearrangement that solves for n, we can go ahead and plug our numbers in. On top we'll have our 0.987 atmospheres times 14 liters. On the bottom our 0.082 liters times atmospheres over a mole times a Kelvin. That's our universal gas constant R. And our Kelvin temperature of 298 Kelvin. Now, when we do this, you'll find that the atmospheres cancel, liters cancel, and the Kelvin cancels, and we're left with 1 over a mole, which unit is the mole. So we multiply our numbers and divide by what's on the bottom, and we get 0.565 moles of chlorine. We can now fill in our before line on the BCA chart. We're starting with 0.870 moles of sodium and 0.565 moles of chlorine. And of course, because this is before the reaction occurs, we have 0 moles of sodium chloride. We have to find our limiting reactant before we can do anything else here. And so we're going to take our number of moles of sodium and multiply it by the mole ratio of chlorine to sodium so that we can find out how much chlorine we need to completely react the amount of sodium we have on hand. So 0.870 moles of sodium times the mole ratio of 1 mole of chlorine over 2 moles of sodium. Again, this is where you use the coefficients from your balanced equation, the only place you use those. And when we do this, our moles of sodium cancel, and we're left with 0.435 moles of chlorine needed to completely react all of the sodium on hand. Well, we need 0.435 moles of chlorine, and we have 0.565 moles of chlorine. So chlorine is in excess, sodium is the limiting reactant. We can now fill out the rest of our BCA table. Because sodium is the limiting reactant, we're going to use all of the 0.870 moles. So on our change line, it's minus 0.870. When we found that sodium was the limiting reactant, we very happily found how much chlorine we were going to use. So we put that into the change, minus 0.435 moles of chlorine. And then because sodium chloride has the same coefficient as sodium, it will change by the same amount, except rather than subtracting sodium chloride, we're going to add it. So as sodium changes by using up 0.870 moles of sodium, the sodium chloride will form 0.870 moles. So it's plus 0.870 moles of sodium chloride in the change line. The after line, we should have no sodium left over. For the amount of chlorine left over, it's 0.565 moles minus 0.435 moles, which would give us 0.130 moles of chlorine left over. And for our sodium chloride, we would have 0.870 moles of sodium chloride formed. Well, we're now ready to solve for how much sodium chloride in grams will form, and also under the new conditions, how much chlorine will be left over. We'll go for the sodium chloride first. We'll take our 0.870 moles of sodium chloride, and we multiply that times the molar mass of sodium chloride for 1 mole of sodium chloride. So 0.870 moles of sodium chloride times 58.453 grams of sodium chloride divided by 1 mole sodium chloride. And this gives us a value of 50.8 grams of sodium chloride formed in this reaction. In order to find the amount of chlorine left over, we're going to have to use our PV equals nRT to find the final volume of chlorine under the final conditions. We have moles, but the conditions have changed. We're not at STP. We're also not at the same conditions when we started because of this highly exothermic reaction. So we kind of have to start over here in terms of finding the volume of chlorine left over. So first thing that we want to do, of course, is to fill out a complete data table. Our pressure now is 1.64 atmospheres. Our volume is what we're trying to find. We're trying to find our volume in liters, so that's our question mark. The number of moles we have left over is 0.130 moles, and that's right from our BCA table. The temperature, much warmer than when this reaction started, 625 Kelvin, and our R value remains the same. That's why it's a constant. We rearrange the ideal gas law equation to solve for volume. It's equal to nRT over P. We did that by dividing both sides of the equation by P. It cancels on the left and you have it there on the right. Then we substitute our quantities into the working equation. So we have our 0.130 moles times the universal gas constant of 0.082 liters times atmospheres per mole times Kelvin times our Kelvin temperature of 625 Kelvin. We're going to divide that by our pressure of 1.64 atmospheres. We always take care of units first because the unit left over will tell us whether we set the equation up correctly or not. Our moles cancel, our atmospheres cancel, and our kelvins cancel. We're left with liters as a unit, and that's what we're looking for. So we multiply our numbers through on the top, 0.130 times 0.082 times 625, and then we divide by our 1.64 on the bottom. When we do that, we'll find that the volume of chlorine left over at 1.64 atmospheres of pressure and 625 Kelvin is 4.06 liters of chlorine. Well, we've come to the end of the video podcast series having to do with gas stoichiometry. Well, at least part 2. There will probably be more parts. But I want to leave you with another quote from that esteemed British statesman Edward F. Halifax. Men who borrow their opinions can never repay their debts. I wish you well.